In this video, I'm going to show you guys how you can use the Savart law to calculate the magnetic field at a certain point from a current carrying wire. So we know the second right-hand rule tells us if we stick our thumb in the direction of the conventional current, or that is current that flows from a high potential to low potential, or the positive to negative terminals on the battery, we can blame Ben Franklin for getting the signs of the electrons wrong, causing a great confusion to all of us electrical engineers out there. Anyways, you point your thumb in the direction of that and curl your fingers around like so. It tells us that it creates a circular magnetic field around a specific portion in the wire. This relationship is actually derived from our little formula here, which was discovered by two really smart old dudes back in the 1800s, whose names you can probably guess. Anyways, it's telling us that our change in the magnetic field, or the contribution of the magnetic field at a point P from a specific section in the wire dl, is given by the relationship mu naught, which is just a constant with units newtons over amperes squared, or the permeability of space, times the current in the wire, which we are assuming is constant throughout, divided by 4 pi, times the cross product of our dl, which is as we said, a section in the wire pointing in the direction of our current, crossed with r hat, which is a unit vector that points in the direction of P. All of this being divided by r squared, which is just the magnitude of distance from our two vectors to our point of interest. So let me just go ahead and draw these out on our diagram here to make more sense of this. So let's just choose our point right here to be our dl. Just draw this out. And our r hat vector is pointing in the direction of P. Now let's apply our cross product rule. So put our fingers in the direction of dl and curl them up to r hat, and our thumb is pointing out of the page. So we can denote that our dB at this point is out of the page, or more specifically, this symbol here. Now notice, even if we move our two vectors to the left side of the wire, let's see what happens. Our dl remains pointing left with the same magnitude, right, and our r hat vector is now changing directions to P. So let me just go ahead and redraw that. I can do that better. Redraw that for you right here. Now if we do the cross product again, fingers in dl, cross it with r hat, our thumb is still pointing out of the page, hinting that each little section of our dl, or section of the wire, is contributing a certain amount to the magnetic field in the same direction. So we can sort of add these up to get a magnitude at that point. Mathematically, we can express that by integrating our equation right here. So the integral of dB is now this b equals mu naught. Since these are constants, we can pull them out of the integral. Divided by 4 pi times the integral of dl cross r hat divided by r squared, where r squared, remember, is just the total distance to our point P here. Since this is a finite wire, we need to set our bounds for the integral, or more specifically, we need to clarify when we're starting and where we're stopping on our contributions of our dl vectors, creating our dBs. So let's just call this angle right here, from this line to this line, alpha 1, and this angle right here to be alpha 2. Now actually, before I continue this, I want you to take a look back at our two vectors right here and study that as I move these along our wire, we're sort of trapped in one dimension, or a plane, hinting that it can be expressed with one variable. And doesn't it remind you of a number line, or an x-axis? And that's exactly what we can call that. Now we can express dl as x, or a change in x. So we can actually rewrite this to be dx. And now we can finally express our distance here to our point D, right underneath D here, given by that this is now x. we can say that the tangent of our alpha 1 is equal to our opposite, which is x, over our adjacent, which is d. Multiply our d, and now we're left with d tangent alpha 1 at our point right here. Now we can do the same thing with the other side. If we grab our vectors back here, put them here, and say that this distance right here is also x, and you can say tangent of alpha 2 is equal to x over d. Now finally, we can plug these values into our... Now we need to be careful here. We need to, since each of these x values are relying on a different value, we need a way to distinguish them from each other. And naturally, if you recall the number line, like we have our negative numbers on the left side and our positive numbers on the right side. We can call this to be our origin, or when x is equal to 0. And conventionally, we can call the left of this to be our negative x's, so this will end up being negative d tangent alpha 1, and this will be our positive. In the end, it actually doesn't matter which way you can order these. We'll still get the same value regardless, so let's put our negative sign right there. So moving on from this integral, it would be easier for us to express this in terms of the magnitude of the magnetic field, just so we don't have to deal with any vectors in our integral. So let's rewrite our cross product. Recall that the magnitude of a cross product is equal to the magnitude of dx times magnitude of r hat times sine of the angle between our two vectors. Hang on, let me just go ahead and drag these back to where they belong. So let's call this our theta right here. The magnitude of our unit vector is simply 1, so we can remove this from our equation. And now we're just left with dx times sine of theta. Now let's study our vectors again, and note that as we move these along our x-axis, our r hat changed, meaning that also our angle between our two vectors is changing as well. So now we're just left with this here. Now it's hinting at us that we can express our theta in terms of our x value. So luckily for us, I set it up so that we have a right triangle here, and it'll be easy to identify that the sine of this is simply opposite, which is going to be our d divided by our r. So sine of theta is going to end up being d divided by r, the distance to our point P. So finally, let's rewrite this entire integral and plug in our new values. So here's our new integral here. We're still left with our r variable, which also changed as we moved our vectors along. And same thing with our sine, we can express this in terms of our x as well, utilizing the Pythagorean theorem. So since this is still x, we can call that our r squared is equal to our x squared plus d squared. So we can rewrite this as so. And our r being the square root of our x squared plus d squared. Now our d is a constant, we can pull it out of the integral as such, and now we're just left with our integrand here. This is a little bit tedious, but bear with me. We have a radical with our variable squared plus some constant squared, hinting that if you remember Calc 2, we can use trigonometric substitution. So let's go ahead and just do that and set our x equal to our d tangent of theta, and our dx equals d secant squared, d secant squared theta d theta, where the derivative of tangent is our secant squared. So let's go ahead and substitute those values in our integral. Now here's our simplified integral. Now since we did a substitution, we have to change our bounds as well. So when x is equal to negative d tangent alpha 1, it is equal to d tangent of theta. Now we can go ahead and just divide a d and take the arctangent of both sides to cancel out our tangent functions. So we're left with theta equaling alpha 1 for our lower bounds. And we can do the same thing with the upper bounds and say that it is equal to alpha 1. Now on to our simplification. Recall the trig identity that tangent theta squared plus 1 is equal to our secant theta squared. So we can factor out a d squared from our inside the radical here, d squared times tangent squared theta plus 1. Now we can plug in our secant squared, so this turns into d squared secant squared theta. Now the square root of this will now just be d secant theta. Now we can do the same thing with the other side, but since it's not in a radical, we can just copy this down. Now finally, let's simplify further, so let me go ahead and rewrite this again. Alright, now we're left with this. These d's cancel out, as well as our secant squares canceling out as well. Now we can pull out this d squared from the integrand, and it will cancel out with the d in the numerator, leaving us with just a single d in our denominator. Finally, we're left with our d theta divided by secant theta, and secant theta is 1 over cosine, so this is simply cosine d theta. Finally, we're at a point where we can evaluate our function here, so the integral of cosine theta is just sine of theta, evaluated from our negative alpha 1 to our alpha 2. Rewrite that as sine of alpha 2 minus sine of alpha, negative alpha 1. Now since sine is an odd function, this is equivalent to negative sine of alpha 1, so we can rewrite this even further and simply have our expression here. And let's go ahead and plug this back into our original function. Well, after all that tedious integration, we're finally left with this here. And wow, it just looks like a bunch of numbers, but if we put some values behind our letters here, we can make more sense of it. So let's go ahead and just grab a calculator, and I'll tell you the values to plug in. Let's call our current to be 2 amps times our mu naught, which remember that is our 4 pi times 10 to the negative 7 newtons over amperes squared, and divided by 4 pi. And let's call our d here to be 0.1 meters, so 0.1 times sine of alpha 2. Let's call alpha 1 to be 45 and our alpha 2 to be 30. Let's make sure you're on degrees as well. We end up getting 2.414 microteslas. So let's go ahead and write that down here. 2.414 microteslas, where micro is 10 to the negative 6. And remember, this is the magnitude of our magnetic field at P, which is pointing out of the page. So let's finally just include our little symbol here. Okay, that was kind of a lot, but I have just one more sort of scenario that you guys can work through, or we can work through together. So moving on to scenario 2, we have a circular loop. Now, okay, this looks a little bit intimidating here, but we're still using the same equation. All we have to keep in mind is our new sort of geometry, or we need to set ourselves new rules to sort of form or strategize, I guess, to our problem here. So we have our same D, we have the same R, but however, since our point P is located equidistant to the center at our distance here, our R actually doesn't change as we move our DL vectors along the circular path. So this is a constant. And has a radius R with our same current going counterclockwise throughout the circle. Actually, so let's go ahead and take a look at our vectors here. We're no longer constrained in a flat horizontal sort of like x-axis. We're now sort of stuck in a circular path, hinting that we can call this to be the arc length of the circle. So imagine like we start right here, and these two vectors are traveling along here. We can call a certain distance from our point here to be the arc length. So this will be S, or more specifically, this will be S right there. So we can rename our DL to be DS. And we can simplify this even further by calling ds equal to r d theta. Since r is a constant, we can sort of just pull it out, and we know s is equal to r times theta of the circle. Now actually, before we continue, let's take a look back at our vectors here and do our cross product. So point our fingers in the direction of dl, and then curl them up to r hat, and our thumb is sticking at an angle. Remember that our cross product always results in a vector that is orthogonal to the both of them, meaning that our db vector is pointing at some angle above the horizon from this point. Now, doing a little bit of geometry, our theta right here is equivalent to our alpha, so rename it like as such. And also, let's take a closer look here. Since our r was constant throughout the circle, the angle between our two vectors is always 90, and the magnitude of our cross product includes the sine of the angle between the two, so that would end up being 1 as well. So let me just go ahead and write that down as well. So we have sine of 90, magnitude of our unit vector is just 1, and this is also 1 as well. And we also said our dl is equivalent to our d theta. Let's look at our actual db vector and what direction in the end are we expecting it to be. So since it's at an angle, we can break it into its components. So let's call this our dbx and our dby. Now notice as we move our vectors alongside the circle, our dx has its own equal but opposite in magnitude vector alongside with it, meaning that it ends up canceling out if we go along the full track of the circle. So let's go ahead and just cancel out. And now we're just left with our dby, which is always pointing up, no matter the direction we are in. Now we're just concerned with the y component of our magnetic field. So remember the angle we found here, we can call the sine of that angle to be our dby divided by db. Multiply our db, and now we're just left with our dby. To simplify this further, we can express our sine of alpha to be our opposite, which is going to be our r, right here, divided by our little r, our hypotenuse. So this is equivalent to big R over little r. Finally, pulling this all together, let's go ahead and integrate our equation here, and we're left with this here. So here's our simplified integral. Now remember, we need to set our bounds as well, and this one's pretty simple. We can just call this theta equaling 0, and as we travel along throughout the entire circle, we can call this our 2 pi as well. So let's plug those numbers in. Our r is constant. We can pull this out of the integral as well. And as well as our big r's, our radiuses, we can pull those out too. And simply we're left with our d theta. And we know that will just be theta evaluated from 0 to 2 pi, which is equivalent to 2 pi minus 0. So finally, our by is, I meant to, this is supposed to be by, Our by is equal to mu naught I r squared divided by 4 pi r cubed times 2 pi. Now, simplifies to be 2, and our pi's cancel out as well. So now we're left with the total y direction of our magnetic field at point P is governed by our equation right here. And finally, let's just plug in our values. Let's call our current to be 2 amps as well. Our radius right here to be, I don't know, 0.2 meters. And times 2 times r, let's call this 0.3 meters. Finally, we're left with 1.86 microteslas. Upwards, pointing upwards. So, I mean, that was kind of a lot to digest. Honestly, I just wanted to make this video because I love being a nerd and explaining shit, and this honestly was my favorite part of my my physics classes.